The subject of today's lecture is the strategy of replacing halogenated refrigerants in new equipment and equipment that is currently used, as well as the strategy of selection of refrigerants. Slide 1 provides a diagram that shows the need to reduce the production and consumption of fluorinated refrigerants over time, depending on the state and region. As is known, the Montreal Protocol, adopted a few decades ago, contained restrictions on the use of ozone-depleting refrigerants. In 2016, a supplement to the Montreal Protocol has been adopted, and it limits the use of not only ozone-depleting refrigerants, but also high global warming potential refrigerants. This restriction comes into force in the near future, especially in the European Union. As can be seen from the diagram in the slide 1, the EU countries are committed to reducing the use of high global warming potential fluorinated refrigerants by more than 50% by 2020. Further, the same commitments were made by other countries. Developed countries later entered the phase of reducing the consumption of fluorinated refrigerants, but the requirements for their reduction are quite strict, as can be seen from the slide 1. On the diagram it is a gray line. Developing countries and some other countries, such as India, Pakistan, Iran, and others, have milder requirements to reduce the use of fluorinated refrigerants. Until now, they can still use them, but should already gradually prepare for the transition to the use of low global warming potential refrigerants. In addition to the gradual reduction in the use of fluorinated refrigerants, European countries have decided to ban the use of high global warming potential fluorinated refrigerants in new equipment. This strategy is presented on slide 2. As can be seen from this slide, as of today, in all household refrigerators produced in Europe or produced for the European market, it is prohibited to use refrigerants with global warming potential of more than 150 kg of CO2 per kilogram of refrigerant. The only alternative in this situation is the refrigerant R600A, that is isobutane, that has low global warming potential. Further, in 2020, the use of high global warming potential refrigerants in new equipment, such as small air conditioning systems, as well as the refrigerants with high global warming potential of more than 2,500 in large refrigeration systems, in commercial and industrial refrigeration equipment, is prohibited. Gradually, by 2030, the requirements of this regulatory instrument result to reduce the consumption of refrigerants in the existing equipment. And starting from 2030, even the equipment using refrigerants with global warming potential higher than 2,500 should be gradually transferred to the use of refrigerants with lower global warming potential. At this point, the question arises, what to choose? Slide 3 presents the main types of refrigerants that are currently available on the market and that have to be phased out due to the requirements of the Montreal Protocol. In the short term, a choice can be made between two types of refrigerants: low global warming potential fluorinated refrigerants and so-called natural refrigerants, which include CO2, ammonia, and hydrocarbon refrigerants. The disadvantage of low global warming potential fluorinated refrigerants is that they are rather new substances, synthesized and having a proven technology, but have not yet been sufficiently studied in the terms of their thermodynamic properties and their safety. In addition, the cost of such refrigerants is quite high, and not always the energy efficiency of the equipment in which they are used will be higher than the energy efficiency of the equipment using natural refrigerants, such as ammonia or hydrocarbon substances. Besides, it is worth noting that both groups of substances, natural refrigerants and low global warming potential fluorinated refrigerants, are combustible substances. But the advantage of natural refrigerants is their low cost and high efficiency in the equipment in which they are used. Slide 4 shows the global trend in the use of different refrigerants in various equipment depending on countries. As can be seen from this slide, the most loyal attitude to the use of hydrocarbon refrigerants in various types of equipment is typical for Europe. In European countries today, it is allowed to use hydrocarbon refrigerants in household equipment and small commercial equipment. Standards for the use of these refrigerants in air conditioning systems, heat pumps, and commercial equipment are being liberalized. The only restriction on the use of hydrocarbon refrigerants currently exists only for large industrial equipment. Most likely, ammonia will occupy this niche as a well-studied and quite effective refrigerant. But ammonia, with its good thermodynamic properties, cannot be used in small refrigeration equipment. Therefore, hydrocarbon refrigerants are a good prospect for improving the energy efficiency of small refrigeration systems, such as household equipment, home air conditioning systems, heat pumps, and commercial equipment. As can be seen from the slide, the use of hydrocarbon refrigerants in household refrigeration equipment is allowed in all countries of the world. The standards are gradually being introduced to allow the use of these hydrocarbon refrigerants in small commercial equipment by 2030. The following slide shows a table of single-component hydrocarbon refrigerants that have prospects for use in various types of refrigeration equipment. As you can see, for each type of equipment, for household refrigerators, commercial equipment, large industrial systems, it is offered one or another, sometimes even 3 single-component refrigerants. And the choice of a refrigerant is not obvious. For example, this table shows that both isobutane refrigerant and propane refrigerant can be used in household refrigerators. Although the practice of using hydrocarbon refrigerants in household refrigeration equipment shows that the most widely used refrigerant is isobutane, the use of isobutane is not very advisable in the equipment, such as automotive air conditioners, due to a bit different parameters of the refrigeration cycle implemented in it. And then the question arises, what refrigerant to choose? Currently on the market there is a large number of mixed refrigerants on the basis of hydrocarbons selected so as to provide the similar pressure of condensation and boiling in the refrigeration equipment in order to replace the traditionally used refrigerants. For example, in automotive air conditioners, in which refrigerant R134 is now widely used, the refrigerant isobutane does not suit very well in respect of its boiling point and condensation, but it can be replaced by a mixture based on the refrigerants isobutane and propane, which are combined in such a way as to achieve the required boiling pressure, that is, similar boiling pressure and condensation. Slide 6 shows the dependence of the global warming potential of refrigerants widely used in the market on their density. The density of refrigerants can also be considered as the reciprocal value of their saturated vapor pressure. Conventionally, all refrigerants are divided into several groups according to the pressure of saturated vapor. The pressure of saturated vapor is important for the choice of the refrigerant for refrigeration equipment in which it will be further used, in accordance with the temperature to be obtained in the cooled object. Thus, a group of low-density refrigerants, as shown in the slide 6, has a relatively high saturated vapor pressure and are used in refrigeration equipment to produce moderate cold. If it is necessary to obtain a cold of low temperature level, it is required to use high-density refrigerants, that is, with a lower pressure of saturated vapor. Thus, these refrigerants are conventionally divided into several groups, and as you can see for each of these groups, you can choose the corresponding refrigerant ecofreeze, the composition of which was selected so as to provide the required pressure of saturated vapor and be the most suitable replacement of widely used refrigerants on the market. The characteristic feature of all ecofreeze refrigerants is their low global warming potential. As mentioned above, the European standard now regulates the reduction of refrigerant consumption with global warming potential of less than 150. All ecofreeze refrigerants have global warming potential about 3, that indicates their high environmental safety from the perspective of their impact on climate. In addition to the need to select refrigerants for different refrigeration equipment by pressure in the evaporator, in the condenser, there is another important point, that is, selection of a refrigerant from the appropriate group that will provide the highest coefficient of performance. Slide 7 shows a simplified diagram of a refrigerator and a simplified thermodynamic refrigeration cycle in the enthalpy pressure diagram. The process of the refrigerant boiling, that is evaporation, is the process in which the final product of the refrigerator is obtained, a certain amount of cold. It is depicted by the green line 4.1 on the diagram. The process of compression in the compressor is the process in which the energy is supplied from the outside. Most often it is the electrical energy required for the operation of the compressor. It is the process 1-2. The ratio of the amount of cold produced in the cycle to the work provided for the production of this cold is the coefficient of performance of the cycle. In this case, slide 7 shows the dependence for the calculation of the theoretical coefficient of performance of the cycle. The higher it is, the more energy efficient refrigerator will be. The less power will be consumed to produce a unit of cold in a real refrigerator. It should be noted that this formula is theoretical. In a real refrigerator, a lower value of the coefficient of performance will be provided due to the losses, non-isothermality of the process of boiling and condensation, deviation of the compression process in the compressor from the ideal one, and a number of other factors. But at the same time, the theoretical analysis of the coefficient of performance of the cycles for different refrigerants will allow you to choose the one that is optimal for the given parameters of the refrigeration cycle, that is, the highest one. In the group of refrigerants that provide the necessary boiling and condensation pressure, it is recommended to carry out a simple thermodynamic analysis of calculating the values of the theoretical coefficient of performance with the choice of such a refrigerant that would provide the highest value of the coefficient of performance. It should be noted that the value of the coefficient of performance of the theoretical cycle will depend on the parameters of the cycle, and with different parameters of the cycle, the same refrigerant can provide a higher or lower coefficient of performance. For example, slide 8 presents the results of calculating the theoretical value of the coefficient of performance at the same condensation temperature of 30 degrees and at different boiling temperatures of the refrigerant in the evaporator. In a lower temperature cycle, with the evaporation temperature minus 6.7, the refrigerant R22 provides the higher coefficient of performance. In a higher temperature cycle, with the evaporation temperature 7.2 degrees, the refrigerant R22 slightly loses to the refrigerant R134. That is, the choice of refrigerant should be made depending on the equipment in which it will be used. The important thing when choosing eco-freeze refrigerants is the amount of charge of the substance into the refrigeration system. This applies to small hermetic refrigeration systems such as household refrigerators or automotive air conditioners. Slide 9 presents the results of an interesting study on the assessment of the annual energy consumption of household refrigerators originally designed for the use of refrigerant 134 and refrigerant R600A, and which instead of the traditionally used refrigerant were charged with a mixture of R436A, similar in composition to eco-freeze refrigerant 134. As can be seen, at different operating parameters, at different amounts of the charged mixed hydrocarbon refrigerant R436A, the annual energy consumption of such household refrigerator varies significantly. That is, there is an optimal mass of hydrocarbon-based refrigerant charge compared to the traditional refrigerant charge. In this case, the refrigerant R134A. It is commonly assumed that the amount of the hydrocarbon refrigerant charged into the system is approximately half the mass of the fluorocarbon refrigerants. But the studies on slide 9 show that even a small change in the refrigerant charge mass affects the energy consumption of the entire system. Despite the fact that it is necessary to choose the mass of the refrigerant to be charged, it is desirable to find it experimentally. Even the charge of the refrigerant R436A, slightly varying by mass, leads to decrease in the annual energy consumption of household refrigerators. The results presented on this slide show that both the use of mixed refrigerant based on isobutane and propane and the use of pure isobutane R600 in a household refrigerator leads to decrease in the annual energy consumption that indicates the prospect of using these types of refrigerants in small refrigeration equipment. Slide 10 presents the studies by other authors on the experimental determination of the coefficient of performance in the operation of small refrigeration equipment at the fixed ambient temperature of 35 degrees Celsius in a climatic chamber depending on the boiling point of the refrigerant in the evaporator. Two refrigerants were compared, the refrigerant R22 and the refrigerant R436B, with composition similar to the composition of EcoFreeze refrigerant 134. As can be seen from the results of the experiment, the coefficient of performance when using the refrigerant R436B is significantly higher than the coefficient of performance of the same system when using the refrigerant R22. Besides, slide 11 shows the results of the studies by some other authors that show the operation of a household refrigerator charged with the traditional refrigerant R134A and two mixed refrigerants with different compositions on the basis of propane and isobutane and pure isobutane. Here, the dependence of the daily energy consumption of this household refrigerator is given when it is operating on these four compared refrigerants. As can be seen from this diagram, the most optimal refrigerant is pure isobutane, and mixed refrigerants based on isobutane and propane, although they provide the lower coefficient of performance than the refrigerant 134, but still lose to isobutane in the energy efficiency. But we cannot say that isobutane will be the best refrigerant for all other refrigeration systems. It is necessary to make a choice for each refrigeration system among the available on the market hydrocarbon refrigerants, including considering the use of mixed hydrocarbon refrigerants, selecting a substance that would provide the highest coefficient of performance. Overviews of the studies conducted by different authors, most of them experimental studies, are presented in slide 12. These studies have compared the performance of the refrigeration equipment on the traditionally used refrigerants, such as R134A, R22, and R12, and show how the value of the coefficient of performance of the equipment operating on traditional refrigerants and the equipment operating on hydrocarbon refrigerants differs from each other. As can be seen from the results of the study, the use of hydrocarbon refrigerants, both single component and mixed, can lead to a significant increase in the coefficient of performance. According to different estimates, depending on the parameters of the cycle, what basic refrigerant was used to compare with, an increase in the coefficient of performance can be expected up to 20%. The main scientific works which were used when preparing this lecture are shown on slide 13. Thank you for your attention.